Hi everyone, my name is Alon. This paper is about how humans perceive or interpret saliency-based explanations about textual decisions. This video will be by me and my co-author Hendrik. So basically, the AI community is very interested in explaining the decisions of AI models, right? A lot of people have proposed explanation methods to produce these kinds of explanations. But in this paper, we ask how do people perceive these explanations. And specifically, we show that this is not as straightforward as it might seem. So suppose we had the following setup where we have this NLP model looking at this restaurant review and classifying negative or positive sentiment. And then we have a user who is looking at this decision and they want to understand why the model made it. So one possible class of explanations that is popular is to classify which parts of the input were the most important, right? It can come in the form of the importance numbers for each token in the input. And then the way it's visualized usually to the user is with a heat map, like this. So stronger color means more important. And then the user looks at this explanation and they have some kind of theory or opinion about what the model did as a result of looking at the explanation. So we could assume that the user understands the explanation trivially as is, so exactly the same information in the explanation, but maybe this doesn't happen. Maybe the user understands the explanation with some kind of bias in the perception from what we expected, and we have a couple of reasons to suspect that this might happen. So for example, in anthropomorphic bias or belief bias, we might hallucinate human-like reasoning behind models. So for example, punctuation marks are not very important to us for sentiment classification, but therefore we might underestimate how important they are to models. And similarly, in visual perception bias, for example, longer words have more color to them, so we might overestimate how important they are to models. And lastly, in learning effects, over multiple iterations, we might change how we perceive explanations, even though the explanation algorithm never changed. Right? So just to recap, our hypothesis here is that we have this objective information inside the explanation. Then we have the subjective information, which is how users perceive the explanation. And in this work, we show that these are not the same for our setup. We try to understand why this might happen. And then we try to intervene on this. Okay? So our methodology will be like this. First of all, we will have data collection where we show users these explanations and we collect self-reported importance. Then we have data analysis where we analyze this data. So the way the data collection works is we use crowdsourcing. We show users this kind of a screenshot where we show them the sentence with a heat map, and then we ask them to rate any random word, how important this word was to the model. Then they move on to the next sentence and so on. Afterwards, we have this data of importance perceptions. And then we want to analyze how we can map from the explanation itself into the user perception. So to do this, we need to appoint potential bias confounders. So this is our list. For example, saliency means the explanation itself, how strong the color is, but we also have stuff like word length and sentence length and so on, which we use in the analysis. So the statistical model we train, I will not go into the details, but we use a generalized additive mixed model. Everything is in the paper, but just to give the brief outline, if we have this setup where a user rated the comma here as 4 in importance of 4, then we have our model where we put on the left-hand side the user rating. Then we have our list of factors, and our model will be the sum of functions of these factors, and we train a model to map from the factors into the user rating. Okay. If everything went perfectly, then the coefficient for the saliency factor would be non-zero, and everything else would be 0, and that's how we know that the user was only affected by the explanation when they understood the importance of the token. Okay, and of course we show that this is not the case.
So as Alon just explained, we now have the user study responses and we have the respective statistical model. And then in the following, I walk through the statistical analysis of these GAM models. And the first experiment I'll talk about is the English sentiment study. And English sentiment here just means that we have English language and we frame the explanations in the context of a sentiment prediction AI. And the first factor which we find to be significant, which has a significant impact on user importance ratings, is saliency. And this makes complete sense because saliency is just the color. 0 is complete white, 1 is complete red. And the more red the color gets, the higher the importance ratings are. And this makes a lot of sense. And one note about the y-axis here, you see that this is not 1 to 7, but this is a broader range. And this is a latent scale and can be translated into the 7 ratings, the 7 ordinal ratings we have via cutoff values, which are also estimated as part of the model. So far, we have this effect of saliency, and this is completely fine, and this should happen. But what we will see next is that there are also more factors which have a significant impact on user importance ratings, and this should arguably not happen. The first effect I'll talk about here is the temporal display index. So this just means that over the course of these 150 sentences, which we show to participants, the users tend to increase their ratings over the course of their experiment. In addition, we find a significant effect of word length. So shorter words are perceived as less important as longer words. And this makes also sense because if you think about a visualization, longer words just have a broader visualization area and therefore are just more color area. In addition, we also find sentence length to have a significant effect. And here we see that for longer sentences, the individual words are perceived as less important. In addition, we find that if a word has a negative or positive sentiment polarity, then an increase in either direction also increases the importance ratings. And we argue that this is an example that users impose their own thinking of what should be important to what the explanation communicates to be important. And this shouldn't happen because the explanation tells what the model found to be important, and users' own thinking should ideally not affect their perception of what is important. And then in addition, we also find that the saliency rank has a significant effect, and this just means that if a word has a certain color, not only the color itself determines if it is perceived as important, but also its relation to the other word's color in the sentence. So far we saw quantitative evidence that there are these significant biasing factors. And what we asked next is whether we can also find these biases in the user's comments. And therefore, we had free text fields which users could voluntarily fill, and I want to talk about one here. So the user rated the punctuation here as 3 and said, I'm uncertain why the period at the end of the sentence would be important, so I chose a 3 even though I coded it as red color. And this is again an example of users mixing their own perception with what the explanation is communicating. And similarly, we also have examples for relative judgment, and there are many more in the paper. So this shows that in addition to the quantitative findings, we also have now qualitative indication that there are these biasing factors. And next, what we asked is whether we can also find biasing factors in another language and another task. And therefore, we went from English sentiment analysis to German fact-checking. And what we see in the respective analysis is that we can confirm many factors and also find new factors like significant effects of word position, capitalization, and dependency relation. And for example, capitalization makes a lot of sense because in German the capitalization is different, and it makes sense that there we find an effect. We couldn't confirm the significant effect of saliency rank in this study, but overall we also find that in this different setting we also find these biasing factors, and they were not just present in the first study. As a further generalization step, we went from the random saliency scores we had so far, so we just randomly sampled color values, and we now went to real-world attribution scores, and therefore we used integrated gradients from a BERT model. And also here, this table shows which effects we found to have a significant impact. And again, we can replicate effects like word length, and also some differ, but overall we can see that across languages, tasks, and scores, in each setting we found significant biases. And the next question we wanted to address in the paper is whether we can somehow mitigate these biases. And therefore we propose two visualization alternatives. The first one are bar charts, and the idea here is that we decouple the draw area of for a specific word from its length. So far we had, for example, here in this example, excellent has a pretty big area which it occupies and also has a lot of color, and we found that word length had a significant impact on user importance ratings, and now we use the same bar width for every word, so ideally this should remove the effect. And the second visualization alternative we propose is a saliency correction method, and here we use the GAM models we estimated to define a predicted bias value. So we try to predict whether a word will be over or under perceived, and then we gradually remove this predicted bias to change the color in a way that after being perceived by the user it is kind of understood in the way that the explanation intends to communicate it. And I'll briefly show an example of the correction method here. So as you can see, this sentence is transformed from this version to this version, and the change in colors corresponds to a minimization of a predicted bias of thanks, like an overperception of thanks and an underperception of the three dots here, and accordingly this color gets a bit lighter and this color gets a bit more intense. And we have many more examples in the paper and also technical details, but for the sake of time I'll skip these in this presentation. So now we saw that we have two proposed alternatives, but we also have to test whether they can mitigate the bias. And therefore we ran another user study, and we actually found that bar charts can mitigate word length bias. So a near constant function here means that if you change the word length, there is no change of this factor's influence on user importance ratings, which is exactly what we want. And similarly, the saliency correction mitigates the learning effects of temporal display index. And these are two promising first results, but we also have to say that there are many others that we have to fix, and these are just first steps into a possible direction to fix these biases. So to conclude, what we wanted to find out in this paper is whether the explanation as it is communicated via this heat map explanation by an explainer is perceived in the same way by the explanee. And what we hypothesized is that it is not perceived in the same way, but there isn't perception bias, a biased perception. And to find out whether this hypothesis holds, we first ran a user study and a GAM analysis, and there we found many significant biasing factors like word or sentence length and so on. And then in the second part of the paper, we check if these factors also can be found for another language, another task, and real-world attribution scores. And the answer to that is yes, they also can be found in all these cases. And then the third and last part of our paper was that we try to propose visualization alternatives that can mitigate some of these biases, and we found that bar charts and our proposed saliency correction method can mitigate two of these biasing factors. And overall, the takeaway message of our paper is that to build effective explanations, we first need to understand users and their perception, and we cannot develop saliency scores or visualization methods without taking the user into account. So we want to stress that this is really an important thing towards effective explanations. And with that, I'd like to thank you a lot. And if you have any questions or comments, please feel free to contact us. Thank you.